Okay, so without further ado, so I'm going to tell you today about, I'm going to try to convince you that big data is low rank. So I'll tell you about what that means. I'll tell you about, some reasons why it might be true and some reasons why it might be false, and what to do about it. Okay, so first, what kind of data are we talking about? Here's an example of a data table. So this is one that you might see in a census application. So let's imagine that there's one row for every person, and there's one column for everything that we know about each of these people. So for example, the first person is 29 years old, female. They come from Connecticut, one of the states in the United States. Their income is $53,000 a year, and they have a college level education. And then there's a bunch of other features that I know about these people that I'm not showing. Okay, so for each person in this data table, I know some things and maybe I don't know other things. So for example, I don't know the gender of this 57-year-old from New York, and I don't know the age of this male from California. Okay. So this is a pretty common kind of data table that you might see in applications in this might be a customer database. It might be something that you would see in a politics application. That you have a collection of data of many different types. You've got some things that look like numbers, some things that look binary, some things that are categorical. They take on one of many different values, one for every region or state. You've got income, which is usually positive and heavy-tailed. And you've got education. Okay, so these are ordinal levels. You know that a high school education is less than a college education, is less than a master's degree, but there's no notion of by how much. Okay. So in this setting, there are a bunch of simple tasks you might want to be able to do. You might want to be able to detect groups of people, find typical responses within those groups, identify related features. Maybe it's easy to predict, for example, income from education, or maybe it's not. You'd be interested to know that. And you'd like to impute missing entries. So you'd like to be able to figure out what level of education does this 41-year-old from Nevada have. Okay. And all of this is made challenging by the fact that the data table could have a very large number of rows, a very large number of columns, and it has missing entries and entries of heterogeneous types, right? These entries are not all numbers. Okay, so to generalize this problem, let's imagine we're working in a setting where we've got a data table A that has M rows, one for every, say, patient in a hospital, respondent on a survey, or asset in a financial model. And it has N columns, which we'll call features. And these are things like tests that we've administered to the patients, questions answered by the respondents, or performance indicators for assets in a financial model. So here, the ith row of A is the feature vector for the ith example, and the jth column of A gives the values of the jth feature across all the examples. Okay, so to make any progress on this problem, we're going to need to make an assumption. And the assumption that we're going to make, and we'll justify it going forward, is that this data table is well approximated by a low-rank model. Okay, what do I mean by that? What I mean is that this M by N data table, for this N by N data table, there is some parameter K that's much less than either M, the number of rows, or N, the number of columns, for which I can find a skinny matrix X that has just K columns and a fat matrix Y that has just K rows, so that X times Y is approximately equal to A. Okay, and this is a rather odd statement to make because X and Y are both numerical matrices. Every entry of them is a real number. So X times Y is a matrix with rank K or less. And I'm saying that matrix with rank K or less is approximately equal to A, but A is a data table that has heterogeneous entries and missing values. Okay, so I'm going to need to justify what I could possibly mean by squiggly equals. Okay, but supposing that I can figure out a good interpretation of squiggly equals, my claim is that it would be really great. And the reason is that then I would have one row of X for every example. Okay, so I could consider that row of X, I could consider that row of, well, first I could consider X and Y a compressed representation of the full data table A. right? Instead of, telling someone all of A, I could just tell them X and Y, and they would know A approximately, okay? The second great feature is that there's one row of X for every example, and I could consider that a vector embedding of that example. And there's one column of Y for every feature. I could consider that a vector embedding of that feature, right? So if I wanted to, for example, plot the examples or cluster them, I could cluster the rows of X instead of the rows of A. And that's much easier because these are complete real valued short vectors instead of long rows of a data table that have heterogeneous types and missing values. Okay, so much easier to cluster or plot these than to cluster or plot the rows of A. Okay, and the third great thing about this is that if there's a missing entry of A, I know that according to this approximation, it's well approximated as the inner product between a given row of X and a given column of Y. Okay, so if I want to know a given entry of A, I just take the inner product between a row of X and a column of Y, and I've got it. So why would we do this? Why would we form a low rank representation? Well, the first reason is to reduce storage. So instead of storing A, I could just store X and Y. Another reason might be to understand the data. We could visualize or cluster the rows of X instead of the rows of A. And notice that by choosing K, we could choose K to be 2 or 3 so that it's easy to plot the rows of X, whereas we can't plot the rows of A if they're in a high dimensional space, where we can't look at them directly. A third reason might be to reduce noise. Maybe we actually trust the compressed version X times Y more than we trust the original data because we think the original data is noisy. We might be using this to infer missing data by using the inner product X between X and Y. And we might be using this to simplify data processing. You could use the rows of X in subsequent data pipelines instead of using A itself. Okay, so the simplest setting in which we might form a low-rank model is a principal components analysis. The PCA is a very old problem, and here's how it goes. It works for a data table A. Oh, sorry, for a matrix A. So for this slide, I'm going to assume that this data table is actually a completely observed real-valued matrix of the same size. Okay, and PCA says I'm going to define squiggly equals to mean that the difference between A and X times Y is small in the sense of squared error. Okay, so the sum over all the entries of the difference between Aij and Xiyj is small in the sense of squared error. So you can think of this as like least squares low rank fitting. And people have been doing this for over 100 years. So this first appeared in a paper by Pearson in 1901, and Hotelling gave the name principal components analysis for this in 1933. Okay. One reason why people really like this problem is because it's easy to solve. One way to see, the way we'd probably describe the solution now is that you can form the solution using a top K SVD of the matrix A. So if you have the top K left singular vectors U, the top K singular values sigma, and the top K right singular vectors VK, you can form a solution to this by setting X is equal to U sigma to the 1/2 and Y is equal to the sigma to the 1/2 B transpose. Okay, now that solution is not unique. In fact, you can essentially rotate sort of X and Y, right? Because the only thing that this objective cares about is the product X times Y. Okay, so you can rotate X and Y, and as long as you do that in a coherent way, then you still get a solution. Okay, but it's worth pointing out that there's another way to find a solution to this problem, which is fix a guess for Y and minimize the objective over X. Now fix that guess for X, minimize over Y. Fix that guess for Y, minimize over X. Continue. Okay, this is called alternating minimization. And what's interesting is for this objective, with probability 1, alternating minimization converges down to exactly the same solution that you would get using the SVD. Okay, now for this problem, there's no reason to use alternating minimization. It gets to the same solution, but it's slower. Okay, so you'd rather use the top K SVD. On the other hand, it's a method that's going to generalize much better to other problems. Okay, when we generalize back to a data table instead of a matrix. Okay, so let's move back to the setting of a data table, and for here we're going to need to use generalized low-rank models instead of just PCA. So generalized low-rank model makes 3 generalizations compared to the PCA objective. The first is that instead of minimizing the squared error, xy minus aij, I'm going to minimize some loss function lj that depends on, both aij and the value xiyj, right? So for example, lj might tell you how annoyed I am to approximate the level of education PhD by the value 17, okay? Right? xiyj is always a number. aij could be an ordinal level, a categorical, or something else. Okay. The second generalization is that we're going to minimize not over all the entries, but just over the entries that we've actually observed. So those are the entries ij and an index set omega. And the third generalization is that we're going to add a little bit of regularization. So we're going to say we're going to penalize the rows of x and the columns of y in order to encourage certain kinds of structures. And I'll talk more about that later. Now, once I've made these generalizations, unfortunately, the problem is NP-hard in general. So it can actually be quite hard to get the exact minimum of this objective. And there's actually quite a lot of research devoted to figuring out how to minimize this objective provably. Okay. But if you just want a fast solution and you don't care about provable optimality, you can still fit this with alternating minimization. And that tends to work quite well in practice. Okay. How do you do this? You fix the guess for y, minimize over x, fix the guess for x, minimize over y. There are a couple of nice properties about this. One is that once you've fixed y, the problem minimizing over x actually separates over the rows of x. So you can solve the problem over each row of x in parallel. And same thing for the columns of y. You can parallelize over the columns of y when you fixed x. This means the subproblems are generally quite easy to solve as long as all of these losses and regularizers are convex. And the objective decreases at every step. So that means it's guaranteed to converge as long as the losses and regularizers are bounded below, which they generally are. It's not guaranteed to find the global solution, but it usually finds a very good model in practice. That's particularly true if you initialize it well. So oftentimes you'll initialize alternating minimization using the solution to PCA, where you've transformed your data table into a matrix in some way. You run PCA on that matrix, and then you move to alternating minimization on the true objective that's this generalized low-rank model objective. This method is also naturally parallel over the rows of x and the columns of y, so it scales to extremely large problems. So you can run this, easily on problems that have millions of rows and millions of columns. Okay. Oh yes, sorry, the chat wasn't scrolling, so I didn't see the question. So how do we attain the top k? This is how do you choose the top k, or how do you solve the top k SVD? How do you choose K? Yes, this is one of the biggest problems, I think, with this framework is how do you choose K? I'll get to that in one slide, the sort of most simple method, but I actually think it's one of the biggest problems. Actually, one of the biggest problems in machine learning in general is how do you choose hyperparameters? So I've come to just dislike methods that have any hyperparameters, and I've been working very hard to either develop methods that have no hyperparameters or methods to automatically choose hyperparameters. But the short answer is cross-validation is the best way to choose K. Okay, but we'll get there in a slide or a couple slides. Okay, so loss functions, right? You should think of the loss function also as another hyperparameter, right? The loss function that you choose affects the quality of your approximation of A. And you're not going to choose, right? You might care about, for example, if you're approximating, people's level of education, maybe you'd really want to get the level of education right. And you're going to have a penalty of, you want a penalty of 0 if the level of education is right, and a penalty of 1 if the level of education is not right. Okay, but that's not a loss that's easy to, that you can sort of differentiate or optimize very easily. Okay, so instead, you generally pick a convex loss function as a surrogate loss. And minimize that. So because of the fact that there's a disconnect between the loss that you would pick to optimize and the loss that you might really care about, you should think about this loss function as another hyperparameter and ask, which loss function enables me to actually get the, to minimize the quantity that I'm really interested the best. Once again, this is sort of a general feature of, this is like sort of a general problem in data analysis and in optimization. Okay. So here's our objective. So what kind of loss might you choose? So there are a bunch of natural examples. We can really just turn to the machine learning and statistics literature and look at what are some loss functions that people have proposed that are known to work well for this kind of problem. And what's nice about this is because I've turned the problem from this sort of unsupervised setting into what looks like a supervised problem where I'm predicting a value, right? Predicting, for example, a level of education using a number that actually looks like a standard machine learning loss. Okay, so I can use quadratic loss, L1 loss, or maybe Huber loss for real values. Huber is quadratic for small values and linear for large values, so it's robust but also differentiable, which is a nice property. For Boolean data, for if Aij is Boolean, so for example, male or female, I might use the hinge loss or the logistic loss. If it's ordinal, like level of education, there are a bunch of losses that are quite nice. I like ordinal hinge loss, or this loss I'm calling bigger versus smaller loss, which you can read more about in the package. And for categorical data, I would use either the one versus all loss or maybe the multinomial loss. Okay, and there are actually kind of nice things about if you use quadratic, logistic, and multinomial loss. All of these losses have a probabilistic interpretation, so you can actually interpret them as a generative model, and you can generate imputations from that distribution rather than just imputing the maximum likely, most likely value. So anyway, those are nice things. But basically, what I'm saying is you can go take any loss function you know, and you can plug it into this framework. So it's pretty flexible. For regularizers, generally you choose regularizers to impose structure. Okay, so you might choose if you don't know if you're really just trying to approximate your data table, you'd usually use quadratic regularization, which helps with statistical properties and stability of the estimates. If you want to interpret the rows of X or the columns of Y and try to understand them, then you'll probably want to encourage more structure in those estimates. So you might ask them to be sparse, which you could achieve using a one norm regularization. You could ask them to be non-negative. So you can actually enforce a non-negativity constraint on X and Y and still optimize quite easily. Or clustered. So you could actually ask that essentially that each of the rows of X takes on, there are only, K different possible values for a row of X. And so this ends up producing a clustering of those rows. In fact, if you use the right constraints, constraint on X and no regularization on Y, alternating minimization on this objective can reproduce Lloyd's algorithm for K-means, right? Which is, right, you take the mean of the points assigned to a given cluster, and then you change the cluster centroid to be the mean of those points. Cool. So what's kind of fun about this is it immediately gives a generalization of the standard K-means algorithm to any data table, right? Even a data table that has, non-numeric values. And you have, for example, you could have a robust generalization of K-means using the L1 loss, et cetera, right? And a generalization of K-means that can deal with missing values. So it's kind of nice to be able to see this in a broader framework. It really enables you to make faster progress. Okay. So how do we impute missing data? Given our model, so once we fix X and Y, we fit the model already. If there's an entry, ij that we don't know, how would we impute that data? And once again, we need to use the loss function because the loss function is the thing that connects, right, that maps the real values X, Y with the sort of values in the right space. For example, level of education, A. Okay, so what we do is we take the minimum of the loss function over its second slot, the slot that should be, for example, a level of education, to produce the most likely value. So there's this implicit constraint that the imputed value needs to be in the domain of the loss function for its second argument. Okay, so if you work this out, you'll find that when the loss is quadratic or L1 or Huber, then the imputed value is equal to xiyj. Whereas if the loss is something else, for example, if the loss is the hinge loss, so L of UA is 1 minus UA, the positive part of that. So subpositive means the min of its argument in 0, max of its argument in 0. Then the imputed value is actually going to be the sign of xiyj. Okay, so if xiyj is positive, you impute +1, and if xiyj is negative, you impute -1. Okay, and that's exactly what you would expect for Boolean imputation. Okay, so let's move to an example. Okay, so here's a notional data table. It has 3 chunks of so imagine, so just for this example, let's imagine actually we're back in this hospital example, and every row is a patient admitted to a hospital, and every column is some tests that we've done on that patient. So we've got 3 chunks of tests. The first chunk returns ordinal values. The second chunk returns Boolean values, okay, true or false. And the third chunk, the first chunk is real values. The second chunk is Boolean values. And the third is ordinal values on a scale from 1 to 7. So for example, what is your pain level on a scale from 1 to 7? Or how satisfied were you with the service at the hospital today? Okay, but unfortunately, something bad has happened to our hospital information system, and we've lost the results of 2 of these kinds of tests for half of the patients. Okay, so rather than admitting our mistake, what we're going to do is we're going to try to impute that data. And I should say, actually, this is synthetic data. So this is just sort of illustrative. It's not. This is not real hospitalization data. Okay. Okay, so we can try imputing it using PCA with a quadratic error. Okay, so treating all the entries as numbers and using a quadratic loss. Here's the imputations that we get. It looks plausible, looks close enough. And if you examine the error, so here I've got a color scale where green is 0 error, yellow is error of unit error of 1, and other colors are other values. So you can see that the error, particularly on the entries that were left out, it's actually pretty good, right? It's mostly green with some yellow. Okay, I'm also showing the error on the other entries, right? So you wouldn't generally, impute those values, but it's kind of interesting to see how well the loss fits those values. Okay, but if we use a loss function that's adapted to each kind of data, so I'm calling this a generalized low-rank model. So it's using a Huber loss on the real values, a hinge loss on the Boolean values, and an ordinal hinge loss on the ordinals. We're actually able to achieve an error that's much lower. It's about a third lower. Okay, so there's much less yellow, more green, and particularly on the sort of on the training set, we're able to approximate it much better. Okay. So all of this is implemented in a Julia package that anyone can download, install, and use. It's quite simple. So for example, to fit a rank 5 generalized low rank model, you can do it in 2 lines of code. So you take your data table A, you initialize a rank 5 model, and you fit it. Okay, so very easy. This is the syntax if you don't want to have to choose the loss functions, and this will just choose default loss functions. Of course, there's also syntax to choose the loss functions yourself. Okay, so how do we validate the model? How do we choose the model parameters? So the rank K. How did I choose K in the last experiment? I chose it exactly in this way. So I'm gonna tell you. Say cross validation. And there's another parameter which is how much regularization do you want? Okay. So the simplest way to do it is to just leave out some fraction of the entries and use the model to predict them. Okay, and then you can say, for what value of these hyperparameters, k and lambda, am I able to make the best prediction on the held out entries? Okay, so this is just simple cross-validation. The nice thing is that you can do cross-validation because the method can handle missing values. Okay, so as a function of, so you can see, as a function of the regularization parameter lambda, which here I'm varying between 1 and 5. If I choose a rank that's too small, so this is a synthetic data set that has true rank 3. If I choose a rank that's too small, like rank 1, I don't fit the data very well for any regularization parameter. Same thing for rank 2, I don't fit the data very well. But if I use rank 3, 4, or 5, I actually can fit the data quite well. If I choose the rank exactly right, so k equals 3, then I see actually I don't want any regularization. But if I've used a rank that's a little bit too high, I end up wanting a little bit of regularization. So the minimum for, say, the k equals 5 curve is around regularization parameter 3. Okay, so this is a pretty sort of simple and easy way to choose these hyperparameters. The real downside of choosing hyperparameters by cross-validation is it means you have to train a bunch of models in order to choose that hyperparameter. Okay. Okay, so let's see what we can do with this model. So these are applications on real data now. Okay, so let's look at a real hospitalization example. So this is data that comes from Stanford Hospital, and it's very similar to the synthetic example I told you before. So every row represents a single hospitalization, and we know patient demographics, we know what diagnoses were made, we know what procedures were done, and we know comorbidities. That means other diseases that the patient has. Okay, and if you try to fit this data table with either PCA, so that means quadratic loss, or generalized low rank model, you can look at the error that you get as a function of the model rank. Okay, so as we increase K. And this is the held out error. Okay, so this is the cross-validated error. And so you can see, number one, that the error values are really small. So that means we're actually able to predict the entries in this data table quite well. And that the error is decreasing as a function of the rank. So we're actually getting better and better and better approximations as we increase the rank. But one thing worth noticing is that if you use PCA, that's this yellow line. Okay, so the improvement is slower than if you use a generalized low rank model that has loss functions adapted to each kind of data. Okay. But here, I mean, I guess what you'd say is the true rank of the data might be even larger than the maximum rank that we showed here, 40. Right? You're not overfitting, right? You're getting better and better approximations as you increase the number of parameters in the model. Okay. I'm going to skip this example because we're running slow. Okay, so I'm going to move on to a stranger example, and that's the example of automated machine learning. Okay. So in this problem, I'm going to construct a data table in order to, so I told you that I really hate hyperparameters of a model. I hate having to choose hyperparameters. It takes a very long time to choose hyperparameters. So I got interested in automated machine learning, which is how do you automatically choose a machine learning model and hyperparameters to fit a new data set well. Okay, so the method that I'm going to tell you about for automated machine learning uses what's called meta learning, which means I'm going to run a bunch of experiments on a bunch of training data sets, and I'm going to use the results of those experiments to choose a machine learning model and hyperparameters really quickly when a new test data set comes along. Okay, so I'm going to start with M data sets. So think, I could go out to the UCI repository and get a bunch of data sets. Okay, and I'm going to choose N machine learning models. So think about these as maybe scikit-learn models, each with a given choice of hyperparameters. So for example, decision tree with a maximum depth of 5, or a lasso model with a regularization parameter of 2.7. So given those M data sets and N machine learning models, I'm going to fit each model on each data set and measure the error of that model on that data set. Okay. Now I'm going to use that to form a data table A. So it's going to have one row for every data set, one column for every model. Okay. And the entry is going to be the error of that model on that data set. Okay, and I could use cross-validated error. I could use balanced error rate. There are a bunch of different notions of error that I could use, and this approach works similarly for all of them. Okay, now I'm going to use my low rank framework. Okay, so I'm going to try to factor this matrix of data sets by models into a low rank matrix. So I'm gonna factor it like x times y. So there's one row for every data set, and there's one column of y for every model. Okay. Now, if a new, and of course I get to control the rank, I get to control K. Okay, so now if a new data set comes along, I should think of that like a row of this data table that I don't know. Okay, now I would love to know the value of every entry in that row, because then that would tell me how every model would perform on my new data set. And I could just pick the model that corresponds to the minimum error. Okay, but I don't know. On the other hand, in this factored space, a new data set just corresponds to a new row of X, and I get to control the rank. So maybe I've set that the X has just 2 columns. Okay, so there are just 2 parameters to learn over here. And if I knew those 2 parameters, I could multiply the corresponding 2-dimensional vector by Y in order to predict how well every model would do on my new data set. Okay, so this is awesome because there are just 2 parameters to estimate. So how do I estimate these 2 parameters? Well, why don't I try running some of these models on my new data set? And I don't have to run all of them, just a couple, right? Just more than 2, really. So I can use this data to figure out what this parameter should be using a least squares regression, right? So I'm finding the row of x that when multiplied by y produces the values that I actually observed for my new data set. Okay, so once I have that guess of what that new row of x is, I can multiply by y to get predictions for all of the, for how well each of the models I have not tested will work. Okay, so that's the result. Right, so you should think of the rows of x as dataset metafeatures, the columns of y as model metafeatures, and then the inner product between a given row of x and column of y as the predicted model performance of that model on that dataset. Okay, so this is kind of shocking to me. Like it seemed like I wasn't sure that automated machine learning, right, that these sort of error matrices should be low rank. But in fact, if you plot their singular values, you'll find that the singular values are decaying. Okay, so as a function of, if you can plot the entire spectrum, the singular value is a function of, which singular value it is. So you'll find it's not that it's exactly low rank, right? These singular values don't go to zero. Okay, well, they go to zero, but they don't get there. But most of the energy of the matrix is contained in just the first couple of singular values. So you can actually approximate that error matrix quite well using an extremely low rank model. Okay, so, but this does tell you, it's right, that if you had time to run more models on your data set, you could use a higher rank, right? You'd have enough time to run enough models to estimate that many parameters. But if you don't have much time, then you'd better use a lower rank model so that you don't have to run as many of these machine learning models on your data set. Okay. Okay, so then the second question, right, in order to turn this into a method for automated machine learning, is we need to decide which experiments to run, which models should we run on a new data set in order to predict its data set meta features. Okay, so let's think about this, right? So we're really trying to find an unknown vector x, right? And we've got some set of measurements yj. Okay, so these are the model meta features. Okay, and we know that we're going to take measurements of this unknown vector x using the inner product with yj. And just for the sake of argument, I'm going to suppose that the values that we get, so by running this model on this data set, are equal to the inner product of this unknown vector, the data set meta feature, with the model meta feature, up to some error that's distributed as a Gaussian. Okay, so it's actually completely unreasonable that the error should really be distributed as a Gaussian. But it's useful for being able to derive a notion of which models we should use for our experiment. Okay, so let's just go with this for now. But essentially, I'm modeling the difference between the true error matrix and the low rank model as a Gaussian perturbation. Okay. Now, given that set of measurements, I can estimate this unknown vector x by least squares. Okay, where this matrix y is just the collection of the measurements that I've performed. Okay, the models that I've run. Okay, so under this model, right, under this Gaussian assumption, the expectation of my estimated dataset meta feature is actually equal to the true unknown vector x. And I can compute the variance of this estimator as well, and the variance is just given by the outer product of these measurement factors, summed up, and then the inverse of that. Okay, so this tells me, a bunch of really interesting things, right? So the variance of my estimated dataset meta feature is going to be smaller if I choose more measurements. More measurements is always better. And if I have to pick a measurement, I want to pick measurement vectors yj that are mutually orthogonal, right? I want them to span, right? I want them to have as large a volume as possible in the space, right? Measurement vectors like this are going to work less well than measurement vectors that are arranged orthogonal to each other. And in particular, if there were some direction in space that I had never measured, then the variance of my estimator x hat would be infinite along that dimension, okay, which makes sense. Okay, so if I'm going to turn this into a criterion to choose measurements, I'm going to need to scalarize it in some way. And the way I do that is with the log determinant, okay, which is, and this is an old idea called de-optimal experiment design, okay. So what I'm going to do is I'm going to introduce an indicator vector, Vj. So it's going to be 0 if I don't choose that measurement, and it's going to be 1 if I choose measurement j. Okay, and then I'm going to write down the variance of my estimator, right, is this quantity, sum of Vj, Yj, Yk transpose inverse. And I'm going to minimize that variance, this scalarization of the variance using the log determinant. Okay. And now that I've got this sort of optimization formulation, I can also introduce any constraints I want. So here, the constraint that I'm going to introduce is that the total time it takes me to run these experiments, to run these machine learning models on my data set, is going to be bounded. Okay. No, it's not, and I'll get to that in a moment. Thank you. The minimization is not computationally feasible. Okay, so, but this constraint says the sum over the measurements that I do times the time that I expect it to take to run that measurement should be less than my runtime budget. Okay, so I always like to write down the problem first and then figure out how to solve it fast. Okay, so that's the problem, and you're right. This is not computationally feasible because this is a semi-definite program with binary variables, and there are packages for solving problems like that, but they are very, very slow. Okay, so what we do is we've tried 2 different ways of solving this problem. One is you can relax it to a semi-definite program by relaxing this binary constraint to be Vj in the interval between 0 and 1. And you end up with, actually most of the Vjs end up being either 0 or 1, and the ones that are in the middle, you can just round to either 0 or 1 in order to get a sort of selection, okay? And then the second approach is you can use a greedy algorithm, okay? So you can just pick the measurement j that most reduces the subjective, and you keep on picking the measurement j that most reduces the subjective. Okay, weighted by somehow the cost of that measurement as measured by the time. Okay, so we developed a greedy algorithm for this, and submodularity of the subjective actually guarantees good performance for that greedy algorithm. Okay, the next sort of important piece of this puzzle is you need to estimate the runtime for each of these algorithms, and we actually did that just with a polynomial regression on the number of features, the number of samples in the data set, and the log of each of these things. So if you use polynomial regression up to order 3 in those features, actually you can estimate the runtime of almost all of these machine learning models quite accurately. So here I'm showing a plot where the x-axis is the actual runtime of the model. The y-axis is the predicted runtime of the model according to our polynomial regression model. And these black lines are showing when the prediction is within a factor 2 of what we said it would be. Okay, and within a factor 2 is pretty good given that the range of these runtimes is ranges over 15 orders of magnitude, right? And you'll see that actually 90% of the time we're able to predict the runtime within a factor of 2. So that's pretty good. Okay, so the runtime prediction is not too bad. Interestingly, the ones that are the hardest to predict are the sort of the linear models. So linear SVM or kernel SVM are the ones that fall outside of these lines the most, and that's because the runtime depends strongly on the condition number, which you can't estimate so simply. Okay, so you can put this all together into a automated machine learning system. Okay, so when a new data set comes along, what do? You start with a very low rank model. So say start with k equals 2 or k equals 3. You choose the set of machine learning models to run on that data set using this time-constrained experiment design framework. You run those models, you estimate the data set latent vector, you see which a machine learning model was predicted to be the best, you choose that model, run it, return that as your answer. Okay, now if you have extra time left over, you increase the rank and you repeat the procedure. Okay, so this allows you to produce good machine learning models very, very quickly, but keep improving your model as time goes on, because we know this matrix isn't really low rank. Okay, so if you have more time, you can fit a higher rank model, you can do better. Okay, so our system is called OBO. That's the red line. So you can see as the runtime budget increases, the red line is decreasing. So it's getting better and better and better errors. And that's true both on the set of data sets OpenML and on the set of data sets from UCI. Okay. In comparison, a state-of-the-art automated machine learning method, AutoScikit-learn, really returns no answer until 16 seconds have elapsed, and then it produces an answer that's about comparable with the answer that's produced by OBO. We also tried out a baseline that we're calling random here, where instead of choosing machine learning model, so it's actually the same as our framework, except instead of choosing models to run on your data set given by optimal experiment design, you just choose random models that are predicted to run within the right time. And you can see that does almost as well as OBO, but not quite. So the experiment design way of choosing which models to run is actually quite important. And you can see that OBO is generally ranked the best. It produces the best estimates actually at all times. Great. Okay, so okay. Well, I'll do why low rank, and then if people want to stick around, I can also tell you what's beyond low rank. Okay, but I think yeah. So I'll go in. I probably why low rank will go into like for another 7 minutes, and then if you want to stick around, then you can also hear about some models that are beyond low rank models. Okay. Let me get some water. Okay, so we've seen that low rank models have performed actually sort of surprisingly well in a bunch of different domains. And, I've shown you two. I've shown you examples in medicine and in automated machine learning. But I've seen this happen in, in retail, in recommendation systems, and in scientific measurements, in scientific simulation, really a fantastic array of matrices are low rank. And I actually started almost getting used to this. And anytime someone would tell me about some new data problem, I would say, well, probably it's low rank. So you might as well, try these low rank techniques, and you'll be able to speed up your computations and impute missing data and reduce noise, and everything will be great. And at a certain point, I started wondering, why? Why are all these matrices low rank? Okay. A conventional explanation is that there just aren't too many features that matter about every say you're in a setting where every row of the data table is a person. And they say, actually, you can describe the person using a small number of features, like every person is very simple. Or, if you're talking about which I don't know how to evaluate. Is that true? Is that false? I actually think people are very complex. Okay. And certainly machine learning data sets, I don't think it's reasonable to say, no, the machine learning data set really, there are only, 5 numbers that matter to completely describe the machine learning data set. And in fact, that's not what we've seen in the data, right? I showed you that, well, a low rank model fits well if it's better and better and better and better as you get to higher and higher and higher rank. Okay. So it's approximately low rank, but it's not exactly low rank. Okay, so I wanted to be able to explain all of these phenomena and why they happen across such a diverse range of applications. Okay, so in order to talk about this, what I did is I developed this mathematical model for a process that generates data sets that's rather general. And then I showed that when the data set is generated according to this process, it results in a data table that is approximately low rank. Okay, so that's what I'm going to show you now. So our general model that I think is plausible for most data tables is that the data table is generated by a latent variable model, by which I mean there's a latent variable alpha I for every row that comes from some set alpha, okay? But this alpha could be extraordinarily high dimensional. And there's a latent variable beta j for every column that comes from some set beta. But once again, it could be extremely high dimensional. So that aij, the entries you observed, are generated by some function g of alpha I and beta j. Okay, so in the case of automated machine learning, right, alpha I might be the entire data set, beta j might be the code in scikit-learn for the machine learning model, and G is Python, okay, Python that runs that machine learning model on that data set. Okay, so you can see like these could be very complicated objects. Okay, So what are some examples of a latent variable model? And I'm going to tell you some simpler examples than that one. Okay, so if the alpha i's actually come from a k-dimensional vector space, and so do the beta j's, that function g, it could just be the inner product. Okay, so the function g of alpha I and beta j is just the inner product between alpha I and beta j. This is an example of a latent variable model. Okay, and in this example, you can ask, what is the rank of the resulting data table A? Exactly, it's K. You've got it. Perfect. Great. Okay, so let's do a harder example. Let's imagine the alpha I comes from the interval 0, 1, and the beta j also comes from the interval 0, 1. Then and aij is going to be some function g of alpha I and beta j. Okay. Can you say anything about the rank of A? Yeah, exactly. It could be arbitrarily high. So it could be the min of M and N. Yeah. Yeah, it's generally full rank. Perfect. Okay. On the other hand, let's consider, instead of the exact rank of that data table, let's consider its approximate rank. Okay, so now I'm going to actually use a notion that's more similar to, sorry, I forget who it was that proposed this idea of upper bounding each of the loss functions earlier in this talk, but I'm going to use a notion of approximate low rank that's very similar to that. So I'm going to say I'm looking for a matrix X that is within epsilon of every entry of A, and that has as small a rank as possible, subject to that constraint. Okay, so I'm going to say the approximate rank of A, the epsilon approximate rank of A, is the rank of the lowest rank matrix that's within epsilon of every entry of A. Okay, so in the sense of approximate low rank, are latent variable models approximately low rank? Okay, and the remarkable result is that they are. Okay, so here's one theorem that states this. So if the alpha I and beta j are univariate between 0 and 1, and the entries of A are generated by a latent variable model with g of alpha I and beta j, and this g is analytic. So each of its derivatives is bounded by some number m. Then the rank of an entry-wise epsilon approximation to A grows as log of 1 over epsilon. Okay, so this univariate latent variable model, it's not exactly low rank, but it's approximately low rank. And actually the rank grows quite slowly as you try to approximate it better and better and better, right? As epsilon decreases, the rank grows quite slowly. The capital M is hidden in the big O notation. So the dependence on capital M is not great. Okay, but it's I've hidden it. You can find it in our paper. Actually, we worked the whole thing out. Okay. So here's the proof sketch, and actually you'll be able to see how, even how M should come in here from the proof sketch. Okay, so for each alpha, I'm going to expand this analytic function g around beta equals 0, just using a Taylor series. Okay, so the difference between g of alpha beta and g of alpha 0 is just the Taylor series. So I've got g prime of alpha 0 times beta, g double prime times beta squared, g triple prime times beta cubed, etc. Okay, now I collect each of these. I notice that I've got something that depends on alpha times something that depends on beta, something that depends on alpha times something that depends on beta. So I'm going to collect the things that depend on alpha into one vector, the things that depend on beta into another vector, and I'm going to write this difference as the inner product. Okay. Once I do this, okay, so you see, I've got this. It's sort of an explicit rank decomposition, right? Because for every row is going to have its own vector like this, because there's an alpha for every row. Every column is going to have its own beta, right? So there's a vector like this for every column, and every entry is given by the left vector for the row times the right vector for the column. Okay. Now, the only thing I need to prove a bound on the rank is to know how many terms did I need in this Taylor series in order to get an epsilon approximation. And the answer is that I need order log of 1 over epsilon terms, using the fact that that this function g is analytic with bounded derivatives. Okay, but you can change the assumption of bounded derivatives to get sort of different results here. Okay. So that's great, but it only works for univariate latent variable models. Okay, and I think the rows could be really complex entities, so I want to allow the latent variables to be vectors. Okay, so in order to make a similar theorem for vectors, I'm going to define what I'm calling a nice latent variable model. Okay, so a nice latent variable model has the distributions A and B have bounded support. The function g is piecewise analytic, and on each piece, that muth order derivative is bounded by something that depends on some number m to the mu. Okay, so the sup norm of each derivative can't grow faster than exponentially in the order of the derivative. Okay, this is still a pretty weak assumption. For example, it holds for polynomials or even for exponentials of polynomials. Okay, so I'm going to ask the same question. What is the rank of a nice latent variable model? Suppose that my data table A is drawn from a nice latent variable model. How does the rank of an epsilon approximation to A change with the number of rows and number of columns in that matrix? Okay, any guesses? Oh, well, you guys have the slides. So it grows for sure. How fast should it grow? So what are some reasonable answers? I guess, well, you know that the naive bound on the rank, right, is min of m and n. Okay, so if I told you it grows linearly in m and n, then that would maybe be pretty boring, right? Yeah. Greater than 1 over e. Yes, in epsilon. Yes. So you think it's going to grow more than faster than 1 over epsilon, and I agree with that. So here's the theorem that we were able to prove, is that the rank of these nice latent variable models grows as the log of the sum of the dimensions divided by epsilon squared. Okay, so compared to the univariate case, some funny things have happened. I've introduced a factor that depends on the dimension of the data table. Okay, so a larger data table, I'm saying you should need a higher rank to approximate a larger data table, but the rank doesn't need to grow very fast. Okay, it grows as the log of the sum of the dimensions. Okay, and if you want a high quality approximation, you're in trouble. But if you want a low quality approximation, like epsilon equals 0.1, then that's fine. Okay, so I guess what's interesting here is, right, the naive bound on the rank grows as min of m and n. So for a small data table, you would probably expect that this factor is larger than the naive bound on the rank. Okay, but for a large data table, for m and n very, very large, this thing is going to be smaller and smaller relative to min and m of m and n. So that means that very large squarish, so that means that large squarish data tables are going to look approximately low rank. Okay, so the proof sketch of this is actually very similar to the previous one. I expand every function g around beta equals 0 by its Taylor series. I collect the associated terms, but now, because these alphas and betas are high dimensional, these vectors are actually much higher dimensional, because the second order Taylor term, I have to vec out BB transpose. Beta transpose. The third order Taylor term grows like the dimension of the latent vector cubed. Okay, so this is a very, very high dimensional inner product. In order to get a bound that actually has a rank that's controllable, what I do is I apply the Johnson-Lindenstrauss lemma to reduce the dimension of these vectors and give me a bound on the approximate rank. Okay. I'm going to skip the Johnson-Lindenstrauss lemma, but if you don't know Johnson-Lindenstrauss, it's one of the most important results in high-dimensional statistics, and well worth understanding. Okay, so that's already more than an hour talk. So I'd love to sort of pause and hear if you have more questions, and then if people would like to hear, I'm happy to tell you about models that go beyond low rank, but this is getting very long. Any questions on why are these models low rank? Yes, the low rank here is it's the same as the notion of low rank in mathematics. Though I guess well, okay, it's the same as the notion of rank in mathematics. But here's what what I mean by approximately low rank is that so I call a okay, so so the epsilon approximate rank of A is the value of this optimization problem. Okay, it's the smallest rank of any matrix X that's within epsilon of every entry of A. So that's what I'm calling the epsilon rank of A. And then I say A is approximately low rank if the epsilon rank of A is substantially less than the min of M and N, the min of the dimensions of A. Okay, so this section, so the first section of my talk was all about algorithms that are usable. This section, the Y low rank, this is all about an explanation. So actually, none of this is a usable algorithm. This is just it's almost just a just so story that should make you feel better about expecting that new data sets that you look at are going to be low rank. Okay, and then what should you actually do when you're trying to compute? I would suggest using the same methods that I talked about in the beginning of my talk. Okay, either PCA or generalized low rank models, depending on what kind of data is in your data table. Okay. So really, how do I use this, this argument in this theorem? I use it to justify why I use low rank models in the rest of my research. So I used to, when I was writing a paper, I would say, we're gonna do this thing, and then the next step we're going to use a low rank model, and then I would say, why are we using a low rank model? Why is this okay to do? Why it works well in our experiments? Okay. But now you can say, not only does it work well in our experiments, but this matrix is really, really large, and we know that really, really large matrices whose rows, whose sort of rows and columns are kind of generated independently from the same distribution, should be approximately low rank. Okay, so that's how I use this theorem. Okay. But you can also use it in the opposite direction, okay? And so that's so when I go on, I'll tell you a little bit about beyond low rank and but feel free to go. It's getting really late your time, so you guys should go spend time with your kids. But anyone who wants to hang out can hear about beyond low rank, or you can watch the video later. Okay. So we saw from the previous section that squarish data matrices, so those where the number of rows is proportional to, sorry, I'm switching notation here. So now P is the number of columns. I apologize. Okay, so squarish data matrices, where the number of rows and the number of columns are kind of proportional, are often approximately low rank, and the approximate rank grows as the log of the number of rows plus the number of columns under rather general assumptions. Okay. On the other hand, if you've got a skinny data matrix, okay, where the number of rows is much larger than the number of columns P, those are unlikely to be low rank because P is already very small compared to the log of the very large number of rows. Okay, so they're unlikely to be very low rank. On the other hand, if you've got a really skinny data matrix, right, then you've got lots of observations per column and not many observations per row. So you think you might be able to fit a much more sophisticated model for each column of that data table. Okay, so really a low rank model is not going to be an appropriate model for a skinny data table because of this fundamental fact about rank. The row rank is equal to the column rank. Okay, so if you're using a low rank model, you can't have a more sophisticated model for the columns than you have for the rows. But in the skinny setting, right, you've got much more data for columns than you have for rows. You should be fitting a more sophisticated model per column than per row. Okay, so let me tell you some, how we might think about fitting a high rank, but still structured model. Okay, so given an n by n data table and a parameter k, I'm going to try finding a low dimensional vector z, okay, a vector z in Rk, and a function fj that maps a low dimensional vector to a real value for each column of my data table. Okay, and I'm going to do this so that this function, right, one for each column, applied to the vector z, one for each row, is approximately equal to the value of that entry of the matrix. Okay, so you can see that this sort of generalizes the same stuff that we had before, right? So this low-dimensional vector for the row and this function for the column can be interpreted as a compressed representation of the data table A. You can think of the zi as a point associated with example I, and fj as a function associated with feature j. So let me give you some examples of this what I'm calling a high rank model. Okay, so okay, one is a very simple one where f is the inner product with some fixed vector. Okay, in this case, this model reduces to the low rank model. Another possibility is that the z is a low dimensional vector and f is a polynomial function. Okay, so we might try to fit polynomial functions. And a third possibility is that z is actually a Gaussian vector and f is monotonic. Okay, so this is called a Gaussian copula model. So for polynomial models, here's the kind of picture we might have. Imagine that your data comes from a low-dimensional manifold, right? So let's say it's a one-dimensional manifold of points in three-dimensional space. Okay, so here the number of columns, right, the number of pieces of data is 3. It's the dimension of the space, but the data really comes from this low-dimensional manifold, a one-dimensional manifold. Okay, so you should be able to impute missing values based on so if you tried using a low rank model for this, you would find that the span of all of these points is the full space. So a low rank model will not be able to impute missing values. Okay. On the other hand, so we've developed models for fitting sort of polynomial high rank models to data that can do imputation. So here, what I'm showing is the original incomplete data, where I've left out I've got some missing data values. So I've left out one of these two features. These 3 features. The red points are the original data. The blue points are the data with missing values. If you try recovering this using a low rank matrix completion model, then you can see you don't recover, exactly this sort of the red points. But if you recover it using our method, kernel factorized matrix completion, then you recover points on this a red manifold, almost exactly. Okay. Here's another class of high rank models, and these are called Gaussian copula models. So we developed these in particular thinking about fitting ordinal data. Okay, so imagine that your data maybe really does come from a simple structured model, right? So maybe there's a Gaussian vector z for every row of your data table, but you haven't exactly observed that Gaussian vector. Okay, instead you've observed some function of that Gaussian vector. Okay, and I'm going to assume that so for each entry of the Gaussian vector, there's a separate function that tells you what you've observed about that entry of the vector, and those functions are monotonic. Okay, so what that means is you take the Gaussian value and you might sort of stretch out some parts and squeeze some parts, or in the extreme case, maybe you only observe thresholds. So you would observe whether the value is less than some threshold or greater than some threshold. Okay, so in this case, this model can produce binary values. Okay, so here I'm showing you that if the real data were Gaussian, and then imagine that we threshold it. So 2 thresholds along the x-axis, 2 thresholds along the y-axis. Okay, so now we only know which region between these dashed lines is the data in. Okay, so now suddenly instead of seeing all of these points, we actually only see 7 distinct regions represented. Okay, and if we wanted to know, for example, the correlation between these 2 values, right? The true correlation of these Gaussian values is 0.8. But the correlation between, these ordinal values, right, after we've truncated them, just said what region we're in, is much lower. It's actually less than 0.5. Okay, so the fact that we're observing the data, through this sort of nonlinear transformation obscures our notion of, correlations between values and our ability to impute missing values. Okay, right. So we developed a model that allows you to fit both this the correlation matrix of this Gaussian vector and these monotonic functions. Okay, so you take a large data table, you learn what are the correlations between the Gaussian Gaussian versions of each row, and what function maps you from the Gaussian version of the data to the data that you actually observed. And so you can try this out on any data set, and we found that it worked really, really well for a lot of different kinds of survey data and recommender systems. So here's one example. This is the MovieLens data set. And what we did is we took all the movies, and there were 207 of them, that had at least 1,000 ratings. And we took all users who rated at least one of those 207 movies. So this produced a very, very skinny data table. In that data table, 75% of the entries were missing. Okay, so only 25% of the entries were observed. Then we masked an additional 10% of that data. We fit a model to the remaining data. So I guess only 15% of the data was there. And we used it to impute on that left out 10% of the data. Okay. So if you do this, you can try fitting this with all sorts of models. And there's a lot that have been proposed. So you could try using it just imputing with the column median. And you'll see that the mean absolute error is 0.7 and the root mean squared error is nearly 1. You could try imputing using a generalized low rank model with the bigger versus smaller loss, was what we found worked the best. And you got a substantially better mean absolute error and root mean squared error. But actually the best model for this data table, and best by a pretty significant fraction, was this copula EM model that fits a Gaussian copula model. Okay, and the reason for that is essentially because the number of rows is very small, but the number of columns is the number of columns is small, but the number of rows is large. So you can do better by fitting a more sophisticated column for each model for each column than for each row. Okay, and we compared it to a bunch of other methods for both parametric and non-parametric, and these two did outperform. So for fitting real data sets, I would strongly suggest generalized low rank model for squarish data tables. But if you have skinny data tables with numeric values, you might try a polynomial model. And if you've got skinny data tables with ordinal or binary values, the copula EM model works extremely well. Okay. There's also something worth mentioning here on this MovieLens data table. We tried all these different models. Many of them perform pretty well. Soft impute, generalized low rank model, copula EM, they perform pretty well. But the generalized low rank model uses rank 8. The soft impute model, and these are cross-validated ranks, okay? Ranks chosen by cross-validation. The soft impute model uses rank 99, and the copula EM model uses a full rank covariance matrix sigma. Okay, so although many of them are doing well, their notions of the rank that they're using to do well on this data set with is quite different. Okay, so to me, this is further justification that low rank, like big data, is approximately low rank, but I don't think that it's because these data sets really are low rank. I think that it's a very good approximation to the structure that's there in the data. Milad is asking why not use a Frank Wolf-based algorithm, and so here, so the soft impute method is optimizing the same objective that a Frank Wolf-based algorithm would optimize. So you would get a result that's kind of similar. The difference would just be the computational complexity. So for this data set, it's small enough that we didn't have to really worry about that. But you would get something similar. Yeah. Okay, so in summary, I've shown you a bunch of reasons why you should believe big data is, well, at least approximately low rank. And I've shown you examples in social science, in medicine, and even in machine learning. So I've shown you ways of exploiting low rank to fill in missing data, reduce dimensionality, and to turn big messy data into small clean data by using these low dimensional representations of the rows instead of the original row. You can find code for each of the models that I've highlighted. The low rank models code is in Julia. The automated machine learning code is called OBO. That's in Python. And this Gaussian copula model, we've got versions available in both Python and R. bunch of papers. So here are the main papers that I've talked about. And of course, the work is with a bunch of collaborators who have been really instrumental in making this happen. So thank you for your attention.